Modern language models can process entire books, massive codebases, and thousands of legal documents in a single prompt, feeding them mountains of text at once. This capacity often leads to a simple assumption that given the data, the machine will read and remember every detail with perfect fidelity. But researchers at Stanford University tested this by hiding specific answers, a needle, inside a massive pile of irrelevant text, or a haystack. Their multi-document question-answering tests showed that when the critical information is placed at the very beginning or the very end of the prompt, the AI succeeds. However, when that same answer is moved to the middle of the context window, performance plummets. In many cases, accuracy drops by more than 30%. Expanding a machine's data capacity does not translate to better recall. The physical location of the data determines whether the machine utilizes it or ignores it. This chart visualizes the Stanford results. Plotting document position against model accuracy reveals a distinct U-shaped curve, where performance is strongest at the edges but weak in the middle. This mathematical curve perfectly matches a foundational discovery in human psychology from 1913. Psychologist Hermann Ebbinghaus identified this pattern in his own memory experiments, calling it the serial position effect. He observed that humans possess primacy and recency biases. It is why you likely remember the first and last items on a grocery list, but struggle to recall the items in the middle. The fact that modern AI exhibits the same U-shaped performance indicates that the serial position effect is a shared limitation between biological and artificial neural networks. The AI's tendency to lose the middle isn't caused by a human-like distraction, but by the mathematical constraints of its attention mechanism. Most models use a system called rotary position embedding, or ROPE. This mechanism assigns attention scores to tokens based on their relative distance from one another. ROPE introduces a long-term decay effect. The mathematical attention score weakens as the distance between tokens increases, causing attention dilution. Every irrelevant word acts as noise. These distractions compete for the model's limited attention weight, drowning out the specific target information. Users can mitigate this through strategic ordering, by manually re-ranking the most relevant documents so they appear at the very beginning and very end of the prompt. We can work within the model's existing biases. We can also use markdown headers and bullet points as structural anchors. These create high-contrast signals that help the model's attention mechanism navigate more effectively. A third tactic involves repeating core instructions at the very end of the prompt. This ensures the model's recency bias is aligned with the primary task just before it generates a response. These black box strategies allow us to engineer the data externally, improving recall by navigating the model's inherent behavioral patterns. Developers are also pursuing white box fixes, architectural changes that can be applied to the model without the massive cost of retraining it from scratch. One solution is multi-scale positional encoding, or Ms-PoE. It is a plug-and-play approach that assigns different scaling ratios to different attention heads. Researchers tested this by applying Ms-PoE to standard models and measuring how it affected their ability to retrieve information from the middle of the context. This comparison shows the impact. In these charts, the green bars represent the original baseline, showing a clear dip in accuracy for middle documents. The brown bars show the results after applying Ms-PoE. It effectively flattens the curve and restores accuracy to the middle context information. Another technique, called attention calibration, intervenes directly in the attention distribution to force the model to focus on relevance rather than sequence position. By rescaling how an AI calculates positional distance, engineers can address the architectural root of the U-shaped curve and improve long context utilization. Expanding a context window to millions of tokens provides little benefit if the model cannot separate the signal from the noise. Simply dumping massive amounts of unstructured data, like dense legal records or patient histories, into a prompt will consistently trigger the lost in the middle effect. Using these models effectively requires a shift towards strategic information architecture. This means prioritizing a high signal-to-noise ratio, pre-sorting evidence, and carefully structuring the hierarchy of the prompt. By understanding these behavioral biases and positioning data strategically, we maximize the chances that the machine stays focused on the information that matters most.